We're going to analyze a slightly different formula now. This is a summation that we are going to call a geometric summation. Any summation that looks like a number to the I is what we're going to call a geometric summation. You may have analyzed these in a calculus class and called them a geometric series when that top value was infinity. It turns out there is also a formula when that top value is a finite value. There are ways to derive this that avoid induction. In fact, when you derived the infinite geometric series formula in a class like calculus, you usually derive this formula as an afterthought in that class. This is an interesting thing because our previous things proved only one formula. This proves infinitely many formulas. Any value of r, this formula will hold for. Furthermore, this summation starts at 0. The reason is that in the previous formulas, plugging in 0 either gave us an undefined value because we had division by 0, or 0, which meant that it was irrelevant in the summation. This summation starts at 0 because r to the 0 will be 1. So, just like before, we're going to prove this with induction. So we begin by telling the reader that. We prove this inductively. We then are going to prove the base case. The base case here, because it's n in the natural numbers, is going to be n equals 0. So, for the base case, that summation becomes the sum from I equals 0 to 0 of r to the I. That's just the number r to the 0, which is 1. Let's use the formula on the right-hand side and see what happens. If we plug in n equals 0, we have 1 minus r to the 1 divided by 1 minus r. That simplifies to just 1. So long as r isn't 1, this is something that you need to be careful of sometimes. This formula as written is actually not quite accurate. There are a couple of things that might cause you to be a little suspicious. In particular, r equals 1 and r equals 0. So we're going to add a little caveat to our hypotheses here and say this isn't just the real numbers, it's the real numbers minus 1. Only because our denominator becomes undefined if we plug in r equals 1. This is something that you need to be cautious of sometimes when you're writing down formulas, is you want to make sure that the hypotheses do always hold. So we notice while we're analyzing this that we might be a little suspicious of the hypotheses we were given. Now, though, if r isn't 1, our base case holds. So this is true. So now let's write down our inductive hypothesis. Inductive assumption. We want to assume that the sum from I equals 0 to n of r to the I is equal to 1 minus r to the n plus 1 divided by 1 minus r. Then we want to show that that holds for n plus 1. So want to show that that same formula, the sum from I equals 0 to n plus 1 of r to the I is equal to 1 minus r to the n plus 1, that's n plus 2, divided by 1 minus r. And just as we've done for several examples in the past, we begin by considering that summation, the n plus first summation, and then doing algebra to try to show that it will equal the formula on the right-hand side. So begin by telling the reader you're going to consider that summation. Consider. We're going to write down that summation. The sum from I equals 0 to n plus 1 of r to the I is equal to, just as we have done in the past, we are going to peel off the final term of the summation and write this as r to the n plus 1 plus the sum from I equals 0 to n of r to the I. We then use our inductive hypothesis, so this is r to the n plus 1 plus 1 minus r to the n plus 1 divided by 1 minus r. That's using our formula. This is by inductive hypothesis. By inductive hypothesis. We now have an algebra problem to try to combine this. Let's try and get a common denominator and see what happens. This is equal to Multiply the first thing by 1 minus r, and we get r to the n plus 1 times 1 minus r divided by 1 minus r, plus the formula, which is 1 minus r to the n plus 1 divided by 1 minus r. We need to distribute and add up these things. We have r to the n plus 1 minus r to the n plus 2 plus 1 minus r to the n plus 1, all divided by 1 minus r. Some nice things happen here. We have an r to the n plus 1 and a minus r to the n plus 1. Those cancel. And if I rearrange the numerator, I have 1 minus r to the n plus 2 divided by 1 minus r. Hold on. That's exactly what I wanted to show. Algebra wasn't so bad this time. So we just need to tell the reader that we're now done with the correct reasoning. So the formula, the sum from I equals 0 to n plus 1 of r to the I is equal to 1 minus r to the n plus 2. That's what we just showed, divided by 1 minus r. Thus, the result follows by induction. The result follows by induction. Hopefully, after seeing 3 different examples of this, we can all agree that, yeah, this is the same idea every time. The algebra may change, but the process remains constant. You peel off the n plus first term, use the inductive hypothesis, and then you do a bunch of algebra to finalize your claim. This formula will be used a whole bunch. It turns out that geometric summations show up a lot. This and the first formula are going to be very, very commonly used, so expect to maybe even memorize this formula for how often you will see it.